So let's go to our MATLAB code, right? So we set the initial number of samples, but this is before we do the rejection acceptance method. So roughly half of this is going to be rejected. So if we need a 10,000 samples, which is 100 square, we probably want to start with 20,000. So now, if you run this, I'm gonna get a probability of 1.11, right? With a measure of the error now being 0.1%. So what I'm getting here is essentially saying that, okay, I get a probability of 1.11%, but I should really account for an error bar on the order of 1%. That is, when I run this again, yeah, I do have this a digit vary, right? When I run this again, I also have this digit vary. So between this and this, there is an error variation of 4%, right? That's on the same order of magnitude as my estimate of my standard error of 1%. Remember, my standard error is not a bound of the error. It's not the maximum error, but it's kind of an average measure of the error. So my error can be more than 1%, can be less than 1%, but on average, it's going to be about 1%. All right. Sorry, not 1%, but 0.1%. That's what I was trying to say. Okay, so this is a rough answer, a first quantitative answer of the question, how many samples should I use? Our next task is we want to get a slightly more accurate answer than this. What if I'm tasked to get an estimate of the probability within 1% of an error? Okay, that is, I'm no longer saying, okay, I want to get an estimate that on average has 1% of an error. But I want to get an estimate that I can confidently say that, okay, the probability is within 1% of the error I'm showing here. What you see is that this procedure doesn't give you that, right? When I perform this multiple times, I get actually, well, something that varies more than 0.1%. So how do I do that? How do I further increase my confidence on the accuracy of the result? So we get to estimate the confidence, right? Well, one of the most naive way to estimate the confidence is actually by performing the sampling many times, as we have done here, right? Okay, so if I have performed the sample multiple times, then I get a sense of how much error, how much variation I'm making through the sampling procedure. Then I can provide an estimate of the range of what the true answer might be. But the problem about that approach, which is not really apparent in our example, is here, is the line 18. So line 18 is a simulation that returns you the result of if I crashed or not, or a sample of the random variable you want to estimate, right? In here, it is extremely cheap simulation in the sense that it's just a few algebraic evaluations. In a lot of engineering examples, just computing this for a single sample involves a pretty expensive simulation. It may take a few minutes or even a few hours to perform every simulation. Although nowadays we have a lot of parallel computers, right? You can go to the cloud and ask for 1,000 instances, and you can run the simulation simultaneously on these 1,000 instances. but still it's going to be very expensive if you want to perform a sampling again and again. So we really want to figure out, is there a cheaper way of estimate the confidence of my answer? So this the answer to this question comes in a pretty interesting way. So let me actually first give you a hint of this by looking at by using this example. And in this example, let me actually make my life a little bit easier by changing the crashed simulation from I'm gonna change the number from 80 kilometer to 50 kilometer, right? Then when I perform my samples, I get a probability that is on the order of 30%. Why I'm doing this is going to be apparent in about 10 minutes. Okay, so now I have this, and I want to perform this sampling, right? Let me change let me change back to about 10,000 samples each time, and I'm going to be performing a loop. I'm going to be set my probabilities is equal to an empty array, and I'm going to be sampling for many times. Let's start with 10,000. Go to probabilities, samples. So I'm going to be performing the sampling for 10,000 times. Each time I'm sampling for around 1,000 samples. And what's the histogram of my probabilities? The histogram looks something like this. Okay, it's a distribution that centers around the value and is also higher around the center of the value. And then it drops down in an interesting bell-like curve towards the two ends. So for those who studied probability or statistics before, what kind of distribution does this look like?
Normal distribution?
Yes, it does look like a normal distribution, right? So this is actually something observed in pretty much everywhere. As soon as somebody starts to use Monte Carlo method to produce an estimator, the probability distribution of the estimator most of the time looks something like a normal distribution. Okay, and if we know that the final estimator looks like a normal distribution, and we know the standard deviation of the normal distribution and the mean of the normal distribution, then we know exactly what the normal distribution is. I mean, that's the nice thing about the normal distribution, is that the mean and standard deviation uniquely characterizes the normal distribution.